and everybody. Okay. So, and this is this paper is entitled "Decomposition of Conditional Risk Premium and its Implications for Representative Agent Model." This is a joint work with Jonathan Loudis. He's in the room. Let me start by saying that the topic here is equity risk premium. We know that the conditional equity risk premium is very important. It's a central quantity, key interest that is of interest to macroeconomics, financial economics, and everybody, practitioners, right? So, and it is also a key ingredient to compute the expected return on individual asset if you believe in the KPN, or if you believe in pharma French or anything, any other extensions of the KPN. As you can see, this risk premium is of interest to everybody. Now, the main question is we ask in this paper is how do we decompose the conditional equity risk premium into different components? Okay, so this paper starts with by considering this decomposition. What you see on this slide on the left-hand side is the conditional risk premium on the market. Okay. So what you see on the right-hand side is a decomposition of this conditional risk premium into three components. Each component is related to exposure to a certain region of the distribution of the return. So what you see, the first component here is the risk premium associated to the left tail of the distribution, associated with the left tail of the distribution. And then you have the risk premium associated with the center, and the last one is the risk premium, which is associated to the right tail of the distribution. Now, each risk premium is defined below, as you could see, which is RPS here. S means S is basically, it could be the left tail, which is D. It could be the center or the right tail, which is U. So, and you can see that each risk premium is defined as the difference between the physical moment, which is associated to the set AS, and the set AS here is the set of return in that specific region of the returns distribution. Is a difference between the physical moment associated with AS and the risk central moment, which is also associated with AS. And this is a natural definition of the risk premium. And alternatively, this can be written as an integral of the wedge between the physical density and the risk natural density, okay, multiplied by the excess return. So what you see here is a cool decomposition of the equity risk premium into several components that are related to exposures to various regions of the returns distribution. So our main contribution in this paper is to provide a methodology to compute each component, okay, of this decomposition. So let me emphasize here that this paper is not about equity risk premium decomposition only. So in this paper, we also decompose the variance risk premium. Our methodology is general. So the theory is general. It can be applied to decompose not only the market risk premium, the variance risk premium, but any high order moment. Okay. So, but for the interest of time and interest of to save space, in this paper, we in the empirical work, we focus only on the equity risk premium and the variance risk premium. Okay. So let me continue here. One application of our framework is that we can easily apply it to evaluating asset pricing models. And we know that over the last decade, like not only decade, like over the last 30 years or 40 years, the number of prominent asset pricing representative agent-based models have been used to explain equity risk premium, several times. So the question is, how do we discriminate further these models? How do we learn about different economic mechanisms behind these models? Because they all come with different economic mechanisms, but they all explain the equity risk premium. Okay, so this paper provides a nice application, a nice tool to evaluate these models to see how these various economic mechanisms affect, what is the main implication of these mechanisms, when we think about each decomposition. Okay, so the implication for each decomposition, each component of the decomposition. So when I say asset pricing models, so have in mind, the three classes, the usual classes of asset pricing models. We have habit formation, we have long-run risk, we have disaster risk. I won't get into details of these models because that's not the point here right now, but I might answer questions later on. But what we are looking for is to look at, the implication of the economic mechanism for each component of this decomposition in this paper as an application of our methodology. So in our paper, what we did is that we provide a method also. To be able to achieve that, we provide an approach, a method to estimate this decomposition in each representative agent model. So one key contribution is to provide this decomposition in the data. The second contribution is to propose a new approach to get to infer this composition, this component from each model. And next, we can compare all these two decompositions. So we've realized that we found that the key finding is that the models are inconsistent with the data. They are not getting close to the data. Okay, so let me give you headline results. So I will get back to this later on and give you more details. So here you have many graphs. Okay, so let me focus and go on this, go over this slowly. The first graph, which is the left one, the top left graph in panel A, it has, in this graph, what we did is that we plot the total risk premium, the conditional risk premium, and also the contribution of each component of the decomposition to the total risk premium. So let me mention that on the x-axis, you have the dates. On the y-axis, so here you have two y-axes, right? You have the right one where we have the total equity risk premium annualized in percentage. And on the left-hand side, what you have over there is the contribution. So by contribution, I mean each component of the decomposition I presented earlier divided by the total. So as a result, the sum of all three contributions is 100. So now let me interpret this result that you see on the graph. So you have a dark line, the darkest line here, represents the total conditional equity risk premium. As you can see, it varies over time. It spikes during crisis period or disaster periods or times of distress. And what is really important here is, when you look at, the shaded area, okay, you have the darkest shaded area here that represent the contribution of the left tail of the distribution, to the total equity risk premium. You have also the medium shaded area, that represent the contribution of the center of the distribution to the total equity risk premium over time. And next, you have the lightest shaded area, which on top, it actually represents the contribution of the right tail of the distribution of the market. Okay. So what can we learn from this graph? It clearly shows that the downside, the left tail, okay, the left tail and the center are the major contributors of the equity risk premium over time. So for example, the darkest shaded area contributes to the equity premium. The contribution varies from, let's say, 30% to all the way to 80%, to 40, 45, 50, and 80%. It varies over time. On average, it's close to 45%, or let's say 45%, or 47 or 48. So same for the center, the contribution of the center also varies a lot. And on average, it's about 45%. This is really interesting. Why? So if we try to apply to compute each component in the representative agent model, we see, the difference. So look at the right-hand side, the graph over there in panel B. This is the Bensal and Yarrow model. What you see is that the center is the main contributor of the equity premium, conditional equity risk premium over time. Okay, so the left tail of the distribution has almost no contribution. Okay, the right tail is, we know, we kind of expect that the right tail has almost no contribution. So the center is a major contributor of the equity risk premium here. So is it surprising? No. Okay, but at least this actually tells us what is going on in these models. You can see that this model, even though this model can explain the total equity risk premium over time, if you compare the dark line in B, in panel B, and the dark line in panel A, they are pretty close to each other. But if you look at the contribution, they are not even close. Okay, so it shows that there is a problem also there, right? So now let's move to, it's not a surprise. So let's move to representative agent models that have more, like a lot of amount of tail risk. Okay, so let's focus only on two here. We have more in the paper. So here in panel C, what you have is the model of Beckert, Engstrom, and Ermolov. This is an extension and refinement of the JPE paper. So the main goal of this model is to explain equity risk premium, variance risk premium, and the low persistence of the variance risk premium. Okay? So what we see here in panel C, we look at when you look at the contribution of the left tail, it's not bad, it's reasonable, it's a little bit closer to the data. So the left tail contribute to the, to the total equity risk premium. The contribution is from 20% to 60%, and it's a little bit closer to data when you compare this to Ben-Salle and Yaron. Now, when you look at the center of the distribution also contributes, right? The center is actually represented by the medium, okay, shaded area here on the graph, panel C. So now let's move to the last model here, which is in panel D, which is the rare disaster model of Watcher. So what you see here is that this model, let me tell you that unconditionally, the rare disaster model of Watcher explains, the equity risk premium over time, like the average equity risk premium. Now, over time, you can see that the dark line is a little bit different from the dark line that we get in the data, even though this model can explain the unconditional one. And you can also see that the contribution of the downside is a little bit different, although we can see that, this model also roughly shows that 40%, around 40%, of the equity risk premium is coming from the downside, the left tail over time, except around 2000 period, the time period around 2000. And the center as well, is also a major contribution. So the takeaway from this is that representative agents have different economic mechanisms to explain the equity risk premium.
So let me interrupt you and ask a question here from, now that I've done it, Jonathan's answering it, but now that I've interrupted you, I'll ask it. From Sang-Byung CO, how did you filter out the time series of the state variables in each model? The results in this figure should critically depend upon that.
Yes. So yeah, right. So we need to be fair as well. Okay. So I will talk about this later. Let me just give like a quick answer to that. In different models, sometimes you have two state variables. In other models, you have one state variable. In the Watcher here, you have only one state variable. So here we use the PD ratio. I'm going to explain later. We try to match the PD ratio implied from the data. We try to match the PD ratio in the data and to get the state variable in Watcher. But I will get back to this later on. Okay, that's a good point. So and these have different implications for the way you plot these over time. So I'll get back to this. If I forget, remind me.
Sounds good.
So let me move on. So from this graph, from this slide that you just saw, it means that there's still a problem here, right? So now let me present the theoretical contributions of this paper before we get into the empirical result. So as you can see, investors may have different attitude toward risk associated with different regions of the market return distribution. Intuitively, if you have a distribution of the return, there are three regions of interest: the left tail, the center, and the right tail, right? So, and each model has a different implication for these sources of risk premium, as we saw in the graph. So now, our paper is not just important, our contribution is not just important for evaluating asset pricing models. So think about this. In the whole market, I'm not an expert, but if you look at that, you will see that there are structural products, for example, in the retail market, that have payoffs that are actually associated with these regions that we already defined here. Okay, these products usually investors care about, exposures to various regions of, these projects exist because investors care about exposures to various regions of the market return. So, and investors are willing to protect themselves against downside by paying sometimes high fees, and as a result, the net return on the investment the net return is pretty low, and this is kind of similar to what we are getting with our upside, the last component, which is related to the right tail, the risk premium related to the right tail. So if we have time, I will come back to this, or we can discuss this further. Okay, so now we also provide a methodology to estimate risk premium, like in these asset pricing models, and then I will get into that. Okay, so now let me talk about these regions of interest. Okay, here again, we can make this more general, like we can use 3, 4, 5, whatever. But intuitively, you can see that, we have the left, right, the left, center, and the right data, the regions that are important. So for now, I will focus on this. So let's define X as the return on the market, and AD that you see here, AD here as the region of the return. Again, X here is the gross return, okay? So X bar here is the cutoff over there. And for example, we could use like AD equals to this interval, which means that the net return is below minus 10%, right? So AC is the regions that, is the center of the return distribution. So we have to define the cutoffs, right, lower bound and upper bounds. And AU represent the right tail of the return distribution. Okay, and X bar here is upper cut, like the cutoff, not upper, the cutoff in the right tail. Okay. So, and these 3 sets, AD, AC, and AU are disjoint. Okay, so and A here is more like the positive real line. So as you can see here, we gave an example. This is what we use in our empirical work. So again, but our theory is general. In our theory, we are not using these numbers here. These numbers are used in the empirical setup, right? But our theory is general. So you might ask, why not using like time varying cutoff or all those things? Sometimes you have, you have data issues. So if we assume time varying cutoffs and increase more these, or lower these cutoffs, then we might deal with some data issue availability of data and things like that. So we stick with this. So now, let me define this risk premium. Again, as you can see, the central object here is to be able to compute each component of the decomposition. So now you can see that each component of the decomposition is the difference between a physical moment and a risk neutral moment associated with the regions of interest. So the risk neutral moment is defined as follows. Okay, so and the physical moment is defined as follows. These are more like truncated moment. Okay, truncated moment. Now, for any AS here, it could be like the lower tail, right? It could be the center, it could be the right tail, or it could be the whole real line, positive real line, right? So we define the risk premium on the market as the difference between the physical, right? The component, right? This component of the risk premium. This is a component of the risk premium. We define this as the difference between the physical moment and the risk neutral moment. Okay. So now, when you look at when n is higher than 1, this is how we define high moment risk premium. For example, variance risk premium. For variance risk premium, you set n equals to 2 here, you get the variance risk premium. You set n equals to 3, you get the skewness risk premium. Now you might ask, why using 2 different definitions, n equals to 1 and n higher than 1? This is because the way that we define these risk premium. you could see that here, if you use n equals to 1, the whole thing will be 0, for example, for the positive real line. So these definitions are consistent with the definition of equity risk premium and definition of the variance risk premium or any high order risk premium. Okay, so now this allows us to write the total risk premium as follows. So the total risk premium is the sum of 3 terms, right? You have all these. Is the sum of 3 risk premium. One associated with the left tail, one associated with the center, and the other one associated with the right tail of the distribution. When n is equal to 1, you have equity risk premium decomposition. When n is equal to 2, you have variance risk premium. So now I need to tell you how to recover these components from the data. So I know that in this room we have experts, and they know how to get, how to get some part of it. So what you see here, you have a risk neutral truncated moment. So here as well, you have, risk neutral truncated moment. We can use, Carr and Madden approach. We can use Bakshi, Kapadian, and Madden. We can use, Bakshi and Madden approach to get these risk neutral quantities. Then the question is, how do we recover? How do we extract the physical quantities, right? How do we extract the physical moment? That's, that's what I will present next. Okay. Now, what you see here is a little bit messy. You have an equation on the left-hand side. What you see is an expression for the physical moment, which is associated with the set AS. And we were able to show under non-arbitrage conditions that you can write any physical moment associated with the set AS as, what you see on the right-hand side. It looks like a complicated expression, but it's not really a difficult expression, to digest. So what you can see is that you have risk neutral moment everywhere in this expression, and these are easy to get. So on top of that, you need to specify what is lambda. And lambda is defined as follows, and it's pretty easy to get as long as you have the preference parameters. So the theta case are related to risk aversion, skewness preferences, etc. So now, let me tell you, this formula is not like, it's not like, it's not random, okay? So it's obtained under certain two main assumptions, okay? Less restrictive. So the first one is assuming if you believe that, the hypothesis of non-arbitrage is always valid, okay? We assume non-arbitrage assumption here. And first, that's the first ingredient that we use. The second ingredient that we use is that, every time you want to move from the physical moment to the risk neutral moment, right? You want to turn the physical moment into risk neutral quantities. You need somehow to specify the stochastic discount factor, right? But here we avoid specifying the functional form of the stochastic discount factor. What we did is that instead we use a nice Taylor expansion series in each region to expand the term to get what we need. So there are 2 ingredients. The first one is, the non-arbitrage assumption. The second assumption actually is not really an assumption, it's an approach. It uses Taylor expansion series. So all you need to do next is to be able to specify the risk aversion, right? The skewness preference. As long as you specify these quantities, even if you do not know the functional form of the utility, you can recover the physical moment perfectly at each point in time. Now you might say, okay, then I don't really know the risk aversion. How do I work around that? We have 2 approaches in the paper. The first one, in the first approach, what we did is that we estimated the risk aversion and skewness and other preference parameters using a nonlinear least square approach. In second approach, we did not estimate these parameters. We followed the economic theory by having restrictions on these parameters to derive these quantities. For example, when I say restrictions, we assume in the second approach that the risk aversion is higher than 1, which is a common assumption if you agree with me. Okay, so I will get back to this later. So now, if you have this physical moment, then the rest is easy to do. you can just go to the data and then recover this component from the data. So now, this question is related. So this slide is somehow related to the question that I think is Sion who asked this question. Now, so in the next few minutes, I will try to answer your question, in details. So how do we estimate this decomposition in a representative agent models? So we know that if you look at red disaster models, you look at long-run risk models, you look at habit formation models. In all these models, they have state variables, okay? And if you compute all quantities, the physical moment or the risk natural moment, any quantity depend on the state variables. If you are able to recover the state variables, then you should be able to compute these quantities, macro quantities of moment at each point in time, 1996, 2000, 2004, whatever you should be able to compute these quantities at each point in time. Okay. Then the question is, how do you extract this? How do you extract these state variables? So we take a stand on how to extract the data-implied state variable in each model. Okay. What we did is that we first transformed the data to have the same mean, okay, the same PD ratio mean, okay, as the model, okay, and the same risk neutral moment mean as in the model, okay, and then we try to match the PD ratio in the data and the PD ratio in the model. Second, we also match simultaneously. We also match the moment, the risk premium in the data and the risk premium in the model.
So there's a clarifying question from Sang. Does this mean that you do not use the return time series to estimate the physical moments?
Yes, we did not use the return time series.
All right.
Okay, so that's why I'm saying, okay, so let me clear here. I'm saying that in the model for here, in the model, we did not use the return time series. It's pretty clear. If you look at, let me give you an example. It's simple. Everybody knows about the long-run risk in the Bensal and Yaron. You take that, the PD ratio is a function of two state variables, right? XT and sigma, it depends on which case you use, case 2 or case 1, right? So it means that you have two state variables in that case. So if you have an equation that relates the PD ratio in the data, okay, you have also the risk natural variance, okay, in the data, then you have two equations and two unknowns. So you can recover these quantities. So now let me, if you don't have further questions, so that's how we were able to extract this state variable from the models. Okay. So in terms of data, what we did is that we used, the usual data set, option data from option metric, and it spanned the time period from 1996 to 2019. We use S&P 500 return data and CRISP. And we apply the standard filters that I won't talk about here. Everybody is aware of these filters, but we can discuss them later on, okay? Now, so as I said before, we have two approaches. The first approach is to use a nonlinear least square to estimate the preference parameters and then feed them into the huge formula that I presented before in the previous slides. Remember the messy formula, and to get each decomposition. The second approach is to avoid doing that and to rely on economic theory and say, well, we all agree that the risk premium the risk aversion should be higher than 1. Let's do that. And then there are also restrictions on the skewness parameter and the kurtosis parameter. And these restrictions are consistent with the economic theory, and we provide references on that as well. Okay. So we compared these two approaches and we found that they are pretty, similar. They are almost, they are similar. They are not as that different. Okay. Now, let me just, for the interest of time, let me show you only one picture of the risk aversion. I'm not presenting the graph on skewness and others. Okay, this graph here shows you the risk aversion that we estimated from the data. And on the x-axis, you have the horizon. On the y-axis, you have the risk aversion. These are relative risk aversion. And then these risk aversion are evaluated at a given point that belongs to each region of interest. For example, the left tail, the right tail, and the center. And the blue line is the one that corresponds to the left tail. Okay, the left tail. And the red one is the one that corresponds to the center. Okay, and the yellow one is, I don't know if it's yellow, but it's close to be yellow, is the one that corresponds to the right tail. Okay, as you can see, as when the maturity is 360 days, they are almost close to 1. Okay, but what is really interesting is that if you look at the shape of the risk aversion, the blue is on top of the red, and the red is on top of the yellow, which is consistent. You believe that investors are more risk averse in the left tail region, compared to the center and compared to the right tail. Right?
So let me jump in again. So from David Schreinder, I'll paraphrase this question. Do you use the assumption that the stock market equals aggregate wealth in either of these approaches?
So in our paper, we, if you write down the first other condition from the representative agent, you see that the SDF is a function of, it's just the marginal utility of wealth, right? So you have WT plus 1. So then we assume that the return on aggregate wealth, okay, all we did is that we assumed that, which is common, that the return on aggregate wealth is the same thing as the return on the market. Okay, this allows you to map the WT plus 1 that appears in the marginal utility into the market return. Okay, and this has been used in several papers, in many papers. It's common. So I see your point. Okay, did I answer your question?
Well, I'll let him follow up at the end if he wants to.
Okay, good. So, and we also estimate high order preferences, and these are in the paper as well. And these are pretty consistent with the finding in a paper that appeared in a review of economic study a few years ago. Okay, so now let me go to the results. So what you see here is the market risk premium decomposition when the maturity is 30 days. Okay, so in the left-hand side, like the left-hand side graph, what you see is the total risk premium, conditional risk premium, which is represented by this set RP, RPA, and over time. And this is the darkest line. You also have other lines in the left panel, okay? And these are component of the decomposition of the risk premium over time. Okay, you have RP1 AU represent, this is actually, let's see, this is the yellow one. It actually represents the right tail. You have the red one that represents the center, and you have the blue one that represents, the left tail of the distribution. What we can learn from the left-hand side graph, again, on the x-axis, you have the date. On the y-axis, you have the return annualized in percentage term. So what you could see is that they are all time varying. They increase, sometimes they go down, and that's pretty much what I can say over there. But what is more interesting is when you look at the right-hand side graph, you can see that you can look at the contribution. Again, I already explained what is in the x-axis and y-axis for these graphs. But what is really interesting is that when you look at the darkest shaded area, okay, I already explained it, you see that the downside and the center contribute to the equity risk premium, are the major contributors of the equity risk premium. And then when I say contribution, I mean, it's the ratio of each component, that's what you see here, divided by the total risk premium. Okay, that's what you see. So I already explained this like 3 slides above. So, but let me focus. Okay, let me focus on the unconditional averages. When you look at the table below, you can see that the second column shows the percentage. Okay, A represents the real line, is the total equity risk premium, which is 8.72. AD is more like the average of the component of equity risk premium, which is associated with the left tail, and AC represents the component of the equity risk premium, which is associated to the center. Now, when you look at the last column, what we did here, we compute the average of the ratios. So the ratios that you see in the shaded area, right? We compute the average of these ratios. Okay, that's why you see that the left tail contributes an average about 45%, and the center contributes about 47%, and the right tail contributes about 6%. Okay. Now, again, now let me move to 90 days. So 90 days, what you see in the paper, we have more horizons, but here I'm just for the interest of time, I'm presenting 90 days only here. So what you see, you have a similar pattern, okay, in both graphs, okay, left and right. But there's a little bit difference between these graphs and the previous one. The difference is that you can see that the numbers actually shrink a little bit, okay? So the equity risk premium, it was very high over time, like when it varies over time in the previous graph. Now it shrinks a little bit. The maximum is 40 if you look at the left graph, left-hand side graph. When you look at the right-hand side, shaded areas, graph where you have shaded areas, you can see that also now the downside, when the horizon increased from 30 to 90 days, the downside contributes more to the conditional equity risk premium. The center contributes, less to the conditional equity risk premium. Okay, so this is also important and an important feature in the data. Okay. So the table below shows the unconditional averages. Okay. So as you can see, the downside was before 45% when the maturity was 30 days. When we increase the maturity to 90 days, you can see that it goes to 61%. Okay. As you can see here, it was 45, and the other one was 47. And here it goes to 61, and the center goes down from 40 something to 23. Okay. So now, let me talk about, so far I have been talking about.
Could I jump in with my own question?
Yes.
So are you always using the same cutoff? I think it was 0.9 to define the downside.
Yeah, this is an important question that we got
So it
before.
seems mechanical, right?
We are using the same cutoff because we could have used different cutoff, but because of data limitation, we are using it. Yeah, we are using it, say, the same cutoff here, but we stick to that because of data limitation. We could have used different cutoffs. So, but we need to be careful in choosing this cutoff. Otherwise, we won't have enough data. So I do agree.
So Tobias Sitcher was asking the same question. So I guess there is no consensus at which level of return the downside and upside starts. But since you already look at conditional quantities, it's maybe worthwhile looking at a definition of down, center, up based on conditional volatility, say 1 or 2 sigmas. That would help with comparability across horizons. I guess he's asking a more sophisticated version of my question.
I see. Thanks for that. I think, yeah, I remember a paper that did that, like the bear beta, something. So yeah, we thought about this, having the cutoff that, varies with, the volatility, like, 2 standard deviation below, 1 standard deviation below. Yeah, so we will see what we can do, and at the same time, make sure that we have enough data. If we have data limitation, we might not go further, like, 5 standard deviations, 3 standard deviations. We'll see what we can do. So, but for now on, we stick to a constant cutoff. So
okay, and actually, sorry, now that I've interrupted you, I'll also remind you that it would be good if you could finish in about 15 minutes.
Okay, good. Thank you. Yeah. So here, this actually presents what we see here is that we look at this gives the result on the variance risk premium. So what you see on the left-hand side, these are like components of the decomposition of the variance risk premium. So the numbers are pretty reasonable and consistent with the data somehow. When you look at the right-hand side, we have also the contribution of each component of the variance risk premium as well. As you can see, the downside is a major contributor of the variance risk premium over time. So now, how do we compare the data and the model imply? So this is what we get in the Bensal and Yarrow model. So I will not go over this again because I already explained, what we have in the Bensal and Yarrow model. Okay. So, but let me just go over the table that you see below these 2 graphs. What you see is that you have the equity risk premium unconditional in the data, which is 872, in the model is 566. But what is really important is that the downside contribution is like this, 45, 40, and the center is 47 in the data. In the model, the downside is 148. So this is not new, based on this graph on the right-hand side that you have seen before. So now the next model that we look at is the Bensal-Kirkwood-Yaron. The Bensal-Kirkwood-Yaron, I won't spend time on it because this is a small variant of Bensal and Yaron. So, and it has almost similar implications. So after that, what we did is that we look at the model from Boleslev, Tauken, and Zhu, which is the first one, among the first one, to show the economic mechanism that use the variance risk premium to predict equity, to predict excess market return. So here so far, results are a little bit, are not consistent, are not close to the data. Okay. So now let me go to the duration Yaron model. So what we did is that, again, we get results from the data. We also get the decomposition from the model. And we know that the duration Yaron model is one of the successful model out there that explain, is more like an extension of the long run risk model, okay? But it assumes also like, a high order moment as well. So here, this model is not also close to the data. As you can see, the downside contributes, contribute reasonably well to the equity risk premium over time when compared to the data. But around the 2005 period, there's almost nothing over there. And then also other time period as well. Okay. So now, again, I want to emphasize that unconditionally, this model matches pretty well, the data, the model matches pretty well the data-implied equity risk premium, okay, on average, okay. So now, if we go to the Beckett and Engstrom, I'm going to present two models, the Beckett and Engstrom model without preference shock and one with preference shock. So the difference between these models is that the first one was designed to better explain equity risk premium and variance risk premium. And the second one, which is with preference shocks, it was designed to not only explain variance risk premium and equity risk premium, but also explain the low persistence of the variance risk premium, okay? So what we see is that the downside contributes a lot here, okay? When we compare this to the data, it's not close, but it's more than what the data tells us. And the center contributes by small margin, which is less than what we get from the data when you look at the right-hand side. The upside has no contribution at all. When we go to Beckett, Engstrom, and Ermolov, we can see like, nice result here. So what you see is that the downside contributes to the equity risk premium, and the contribution of the downside is a little bit closer to the data. It's not perfect, okay, but it's closer to the data. The center also contributes to the equity risk premium over time, and but it's a little bit closer, but not exactly what you see in the data. So overall, when you compare all these models, it seems that the one with preference shock seems to be doing a better job in getting closer to the data. So below the graphs, you have also the summary statistics as well. So now the next model is GABEX. So what we see is that the right-hand side, you have GABEX, okay, and again, so this model have more like a similar implication as the Watcher model that I presented before. So again, the downside contributes a lot, except around the 2000 period, okay? And that's pretty much what we get from this model, okay? But let me emphasize here again that although conditionally this model is not close to the data, unconditionally it seems to do a better job, right? Like what you see 872 in the data and 775 in the model, okay? So now this is Watcher. I already explained Watcher before. I won't go over it again. Now, in this table, what we did is that we presented the difference between the risk premium in the data and the risk premium in the model. The difference between each component in the data, each component of the decomposition in the data, and each component of the decomposition in the model. And then we compute also, some summary statistic in parentheses here. You have, it shows numbers here, shows that these numbers that you see on top here are pretty significant. These are component of the risk premium. This is the difference between the data implied and the model in the Bensal and Yaron. This represents the difference between the downside part in the model and the data. And in this part of the table, we compute similar result by using the contribution and not the level, the contribution. So again, this table is here to highlight the difference between the model and the data. Okay, and we did it for the long and risk model, we did it for habit formation, and we did it for disaster risk model, and we get pretty, a significant result. So now, comparing data and model implied variance risk premium decomposition. So if you remember what you have seen before, I have shown you the contribution of the variance risk premium over time, okay, of each component. So here, the darkest shaded area is the contribution of the downside. Look at the left-hand side graph. The darkest shaded area is a contribution of the downside to the total variance risk premium, okay, in the data, okay? And you have the shaded area here, the medium shaded area that represents the contribution of the center to the variance risk premium. But the right-hand side graph is the result that we get in the direction arrow, which seems to be not close to the data as well. Okay. Now, but when you look at unconditional results, this is what we get in terms of, we have minus 1.03, which is the variance risk premium, the total variance risk premium on average. And this is what you see in the model. Okay. Again, the model seems to be doing a little bit better when you look at unconditional result, but when you look at conditional result, okay, it fails. It fails. So this is the model from Beckett, Engstrom, and Ermolov without preference shocks. Again, you can see, look at this. So this seems, if you look at these two graphs, you can see that the left-hand side is almost close to the right-hand side graph. So it shows that the model without preference shocks seems to better explain each decomposition of the variance risk premium over time. Okay, so there's a tension here. Let me emphasize that there's a tension here. They have two models in Beckett and Engstrom. The first one, which is with preference shocks, seems to do a better job in explaining each component of the risk premium. And by this model that is doing a better job in explaining every risk premium, each component cannot do a better job in explaining the variance risk premium. But when you look at the second model, right, the second model, it does the opposite. So there's a tension here. Okay, there's a tension here. So that I want to highlight. So that's what you see. Okay. So this model, which is with preference shock, which actually explains better equity risk premium and its decomposition, has actually a hard time in explaining the variance risk premium. Okay. So there's a tension here. So you can see there is a tension. The left-hand side graph is completely different from the right-hand side graph. So this is the model that we, so how many minutes do I have?
It would be good if you finish in about 5 minutes. We have a hard stop in 10 minutes.
Okay, good. Perfect.
You're done in 10 minutes no matter what.
Yeah, so I'm getting there. Thank you. Thank you. So this is a model from GABEX. Okay, in GABEX, you have the left-hand side. On the left-hand side, you have the variance risk premium and its component. And the right-hand side, sorry, in the data, you have what you see in the left-hand side. In the model, you have what you have in the right-hand side. Left-hand side data, right-hand side model. Okay, so you can see that the darkest shaded area is all over, right, in the right-hand side, which means that in the disaster model of GABEX, the downside is a major contribution of the variance risk premium. You can see this on average is almost 98%. 98%. And this is common. If you take GABEX or you take Watcher, okay, this is Watcher as well, and they have almost similar implications. Let me remind you, okay, I want to be fair here. Let me remind you that in these models, you have one state variable. So, okay, that could explain why also, right? Not only you have a huge amount of downside over the tail risk, but again, you have also one state variable. So now we also compute the difference between the data-implied variance risk premium and the model-implied variance risk premium over time. And we also compute the difference between each decomposition of the data-implied variance risk premium and each decomposition of the model-implied variance risk premium over time. And we also compute the summary statistics. The difference is significant for Russian Yaron, is significant for all these models that have a large amount of tail risk. Okay. So, and the difference shows that these models are not closer to the data. So we also, in the paper, I'm not presenting this here for the interest of time, we also estimate the STF at each date. So we also, our theory also is more general because it says that we can compute any risk premium and any component of the decomposition of that risk premium. So if you set n equals to 0, then you get Arrow-Debreu risk premium. Okay, Arrow-Debreu security risk premium. Okay, this is something that you can we can easily have in the paper. But our paper is more about equity risk premium, variance risk premium, any high order decomposition. So we also thought about having a methodology if you have if you specify the utility function. What is really nice, cool here is that if you know the utility function, if you know the functional form of the SF, or you know the utility function, let's say utility function here. If you know that the utility could be a log function or a CARA or CRA or HARA, then fine. So we have all the expression. We have closed form expressions of all these quantities. There's no need of any approximations in that case. And we provide analytical expression, and we're able also to derive, to go to the data and see what are the implications in each of these cases. So what is really interesting is that we can see that the level of the risk premium is different, if you look at these utility functions, but the contribution seems to be the same. So it seems that, if you compare the contribution in the data-implied result I presented earlier to the mod, like the utility-based result, okay, contribution, they are almost the same. Not exactly, okay, there are a little bit variations sometimes, but they are similar. So that's what I want to mention. So let me conclude this by saying that in this paper, what we did is that we do recognize that we are using non-arbitrage assumptions, which is common in the literature. We also do recognize that we use Taylor expansion series, but again, you can think about this as being model free because we have less restriction than people usually use in getting these things. We propose a new approach, a new approach to decompose the conditional data-implied risk premium into various components. Again, our paper is more like a conditional, we focus on conditional risk premium. Okay, I know that there's a paper by Schreindhofer that is unconditional, right? So if where they try to provide a decomposition in an unconditional setting, is a pretty cool paper. So we also provide a novel methodology to extract the state variables from representative agent model. So why? Because this is really important. If you look at all these representative agent models, they always perform simulations. Okay, let's simulate the state variables here and there. And then with the simulations, let's get the unconditional equity risk premium, unconditional variance risk premium, and other unconditional macro quantities. But all these models are using conditioning variables via state variables. So we need to investigate deeply, these models in details. So how to do that? By just looking at, evaluating these models in a conditional setting. That's the easiest thing to do. So we show that there's a significant difference between the data and the model implied decomposition for the market risk premium, for the variance risk premium. We did not look at skewness risk premium in the data, even though our theory is a general theory. Okay? So our methodology is sufficiently general that it can be used to estimate any risk premium and also Arrow-Debreu securities risk premium as well. Okay. So think about our methodology as a new approach that can be used to provide new insight into sources of variation in the risk premium over time. Okay, over time. Okay, and this actually will help us better evaluate asset pricing models and can be used to, can be used in other applications as well, where we believe that the conditional equity risk premium is very useful. Okay, so thank you, Neil, and thank you, Dimitri and Krish. And thanks to, the participant.
Great, thanks very much. At this point, I'd like to invite everyone to unmute themselves. And, if you have any remaining questions, you're welcome to use your microphone and ask the questions orally. There were a couple of questions in the chat that I deferred, but it might be more efficient for me to let those people ask those questions, since I'm sure they'll do a better job with their questions than I will. So anyway, if you have any outstanding questions or anything you want to clarify, you're welcome to use the microphone.
Hi, Fousseni. This is Sam.
Yeah, hi.
So
Yeah, hi, Sam.
I actually have two questions. First of all, how is this test different really from showing whether these models can capture out of the money puts and out of the money calls? So for example, if you show, if we go back to your figure for Banzhou-Yarrow model, basically all the equity premium is coming from the middle component. And that is not surprising because long-run risk model is log normal model. So it does not generate any implied volatility skewness. So in that sense, whether the model can capture out of the money puts, out of the money calls, I think that can be pretty much the same test that you can actually show out of your decomposition. And for example, if you want to really see whether the downside component is important or not, what you can see instead is looking at the put protected portfolio returns. Then you can see what percentage of the unconditional equity premium is coming from the shock that is bigger than 10%. You can actually construct that. So given that you are actually able to test these models, I don't see, I want to see what is the main benefit. And the second question is, especially when you look at the Wagner model, you can see really weird behavior around 2000 or 2001. And that is really because of the fact that you're using the implied state variables from the PD ratio, because PD ratio pattern is quite different, especially around the NASDAQ boom, right? At the time, the state variables were implied volatilities were high, but at the same time, PD ratio was very high because of the high tech bubble related, phenomenon. So it is a little bit unfair to estimate the state variables to match implied volatilities. If you probably, estimate the state variables to match the at the money volatility, for example, you're going to have a completely different result. So these are the two questions that I have. Yeah.
Okay. So the first question is, what is the benefit of having this decomposition here? I think that is beneficial because, like, your question is marginal. Like you could say, well, why, I could have computed the return on an option and then comparing the data in the model, right? So in the data, and why do I need a decomposition? Remember that investors care about, or we as like, researchers, we care about exposures to various regions of, of the return. We want to know how these different areas contribute to the return. So for example, if I follow what you're saying, like I could have used Todorov's paper, right? And where they have large positive jumps and large negative jumps, and try to use, the combined extreme value theory to estimate something related to the risk premium, right? But what you see here is that you can do those things, but we are doing them all simultaneously, right? We have an approach that decomposes, what is of interest, not just one part of it, what is of interest into different areas, and looking at, what is important at a given point in time, okay? So, and this can be used to, in many applications, not just evaluating asset pricing models. But I do believe that there's a benefit to this. Now, when you say that it's pretty unfair to Watcher, again, in other papers, I was clear that, when I presented the graph from Watcher, I was pretty clear that we use only one state variable, which is the PD ratio. And I agree with you that if you use the PD ratio, you can see, if you look at Gabex and Watcher, you see almost similar patterns, right? So what we also plan to do is that we plan also to, instead of using the PD ratio, we could have used the risk neutral variance. right, Sang? We could have used the risk neutral variance. And if you use the risk neutral variance, I'm pretty sure that the picture will be different over there. So again, at the beginning, I said that we take a stand on how to extract this state variable. So it will be worth it to discuss this by saying, well, this is just, these models have only one state variable. That's why it seems unfair. Because if they have two, they will be close to the others, right? So we'll have a discussion probably, and where we will compute this decomposition, each component, by, instead of using the PD ratio, using the variance risk premium, for example. Not the variance, the risk neutral variance. In that case, you will see something that you would like to see, right? So yeah, I think that's a pretty fair comment. So, and we do recognize that, and then this will be taken care of in the paper. So we want to be fair to everybody, okay? So, and at the same time, provide new insights. So, and then someone else could say as well, so how about instead of using the PD ratio, you could have used something else as well, right? We could have just fit the equity risk premium, right? And the PD ratio, right? So, and we get the difference. So again, regardless to, the assumption, if you use, equity risk premium PD ratio or risk neutral volatility PD ratio, you will see that the data, the model implied result will be different from the data implied result, for sure. Okay, but I think this is a fair question, and then it's something that we can address in the paper by having more discussions over there. I agree, totally agree with you.
Thank you, Fousseni.
Yeah.
Hi, Fousseni.
Yes,
Thanks. I appreciate the advertisement for my paper. So I want to try to make my comment that I asked in the chat a little bit broader. So I think everybody in this audience understands the main issue with estimating conditional risk premium is getting the conditional P distribution. I think my general comment would be to try to give a little bit more intuition for how you do this. So we had chatted about this before, and hence my question in the chat was a little brief. So you need the assumption that the return on wealth is the stock market return. And it wasn't clear to me whether you need this for both of your approaches, but it seems to be the case, right?
In the paper, we assume that the return on aggregate wealth is equal to the market return.
And right? So okay, that's fine. You need to assume something to get the P distribution. But one issue with this is that it doesn't apply in the models, right? But and if I understand what you did correctly, then you don't apply the same approach in the models, because in the models you can compute things independent of this assumption. But it would be nice to see. I think the model we can
compute. Okay. Think about this. Think about our SDF as a projected SDF on the market, something like that. So if the answer that I will give you is that, okay, in the model we have no restrictions, okay, in getting all these results. But in the data, think about, because we have our focus on the equity risk premium is on the market. Just think about everything that you get, like the SDF as a projected SDF on the market, something like that. Okay. So, but I know that someone could say, well, how about having labor or something else or whatever, right? So like, someone could say it's not clear why the return on aggregate wealth should be equal to the market. But I think that's a common assumption that if you believe that suppose that if I use a different asset, here the object, if I use individual stocks, for example, it will be maybe a little bit more different, right? So I need to be careful here. But here I have in mind of projecting, we have, think about our STF, which is a Taylor expansion series of the marginal utility, as a projected, something which is projected on the market. So I totally agree with you that this assumption, maybe what we could do is that we can discuss this further in the model.
I have a quick suggestion, actually. So so the assumption in reality is hard to test, right? But in the models, we know the extent to which it holds. What you do in the data is you use this assumption to extract preference parameters. Yeah. In the model, you know preference parameters, right? So why don't you extract risk aversion in the long-run risk model and see if you recover the number you stuck in? That's a direct and simple test of this assumption and of this approach.
how to estimate the risk aversion in the long run. So how do we pin down the risk aversion?
What you do in the data is to back out these preference parameters based on the assumption that the return on wealth is the return on the market.
Oh, I see.
Right? Can you not apply the same approach in the model, recover the preference parameters to check, do they coincide with what you know to be the truth?
Yeah, but we know that they won't be the same anyway, right? I don't know.
But then, I mean, you can show readers how close you are. If you're reasonably sure, they're not going to be exact. But the validity of this assumption relies on you getting pretty close.
I see.
If you can show me you're pretty close in the models, then I'm more comfortable with the assumption.
I see. I see. So this is well taken. Yeah, I see. We'll think about that and see. I can talk to you again if, if I have some,
We can talk offline, sure.
Yeah.
I mean,
we can talk offline.
Related to David's comment, I think under a disaster risk model, right? We actually assume a patient problem in the post-war sample. So we assume that investors fear the possibility of a rare disaster, but rare disaster did not happen ex post. So if you actually estimate the P distribution using the data, you will never capture the correct P distribution, right? So that is something you should also think about, because the return data that we observe will never capture the true P density that investors face under a disaster risk model. So estimate that P from the data and compare with the implied P from the model will never be the same because of the patient problem, right?
I see. So, but remember that in the data, what we did is that we first estimate the preference parameters, and there's also a second approach where we avoid estimating the preference parameters. We use restrictions implied by economic theory. For example, risk aversion should be higher than 1, and some few other things. Okay. So in the model, I see your point. In the model, we took all the calibrations, everything as given. And then I agree with you that the data will not be the same, data implied result will be different from model. Even today, if you are able to construct the best model out there, right? I'm sure that this model will not match the data. But I think as researchers, what we want is that we want to be close. We know for sure that we will never get exactly what we get in the data. So we need to be honest on that, right? So, but we want to be close because everything is changing, the world is changing, the market is changing. Even if a model does a better job today, okay, over using the past year's data, who knows, 40 years from now, the same model might fail, right? Because, if you use, so that's why I think we will never be able, to match exactly what we get in the data. But what we really need is that we want the model to reproduce the features as close, to be a little bit closer to the data.
I had one more comment about that. So the main question is, in particular in disaster risk models, or even when we estimate our decomposition in the data, you're concerned that if we don't actually, even if investors fear crashes will happen, but if they're not realized in the data, we may have inaccurate estimates of the preference parameters because we don't actually observe those realizations. What I'll say though is that we did do, we looked at this to the extent we could by estimating our preference parameters in our first unrestricted version of the decomposition, both with and without the financial crisis data included. And our preference parameter estimates are actually pretty stable to that. So the point is our decomposition, our data-implied decomposition, is dependent on the preference parameters we estimate, or the ones that we take from economic theory, as Fousseni mentioned. But I think that those estimates aren't super sensitive to at least including or excluding the crash that we did observe in 2008.
Did we answer your questions? We can talk more about that offline or on Zoom as well.
Yeah, I think it's going to be a discussion that is going to remain very lively for